The next talk is by Professor Tsvika from University of Haifa and Untitled Chapter. Professor Tsvika is a professor and former head of the Department of Information Systems at the University of Haifa at Israel. His main areas of research are ubiquitous user modeling and intelligent user interfaces. For over 3 years, he is leading a research group at the University of Haifa, focusing on active museum, applying novel computing and communication technology for supporting museum visitors. Tsvika and Davidal, the floor is yours.
Finally, after managing to work it out, on the end-user perception of algorithmic fairness, we will talk about explainability, fairness, and in between. This is actually the PhD work of Avital Schulner under my supervision. But I'm presenting. Avital is busy in the lockdown managing her kids and the family. So we'll try and I will try and do it for her. When we're looking at the various buzzwords like artificial intelligence, machine learning, neural networks, deep learning, etc., all those nice terms that are appearing in those shapes in front of us, we can see that these techniques are used for various daily applications. Natural language processing is used by our intelligent agents, Siri, Alexa, etc. Computer vision is used by Waze, for instance, or other mobile smart glasses. Robots are using, you can see one robot here, but robots are widely used in production lines. So actually, artificial intelligence is a part of our daily life everywhere. And if we look behind the scene, there is one common theme for all these applications, and they are controlled by algorithms. And the algorithms are the part that actually make everything work. So let us start by discussing and presenting what an algorithmic system is. When we are considering an algorithmic system, we can look at this schematic description or schematic presentation. We see the algorithmic model itself, which is the actual computational part of the system. But this algorithmic model uses some kind of a training data for building the actual model. It is configured by its users, which we call third parties. It is applied to an input and provides an output. And we are looking at this as a very simplistic model of an algorithmic system, which we know very little about how it is built, how it works, how computational aspects work in such a system. These kind of systems are used for multiple daily applications. They filter job applications, they analyze credit requests and deny or approve them. They even take judicial decisions whether to let prisoners be sent out on parole or remain in jail. They are used for medical decisions. They are used for maintaining us safe while driving. So we can see algorithmic systems wherever we go, everywhere, whatever we do. And obviously, the very, very trivial examples are our mobile phones or command assistants, our shopping assistants, or news recommenders. If we consider job filtering systems and we overlay it on the schematic model of the algorithmic system, we can see that there is the algorithmic model, whatever it is. It uses a database, a training data of candidates' CV and their success level in being assigned, being accepted to work or not based on their CV. The algorithmic system is being configured according to the company's employment guidelines. What are their preferences and guidelines about filtering applications? And the system gets us an input, a candidate CV and a job description, and decides whether the candidate may be considered for hiring or may be rejected. And the output is a recommendation score or a decision of the system about this specific candidate, whether to hire this candidate or not. Another application may be a medical decision support system. And again, it is the same schematic representation. There is a database, there is the training data, which is disease, symptoms, and actually past cases and associated treatments, and whether they were successful or not. And there is the third-party configuration, preferences about medications to use according to costs, other policies about medical procedures, medical guidelines. So the system is configured and the system is trained by past experience. And then the current patient symptoms are being analyzed, and according to the previous cases, whatever the system learned, and the guidelines that guide the system according to the HMO procedures and the guidelines, produces a recommended treatment. And the physician may consider those recommendations while subscribing treatment to the patients. So you could already notice the main problem of those systems. There is a big black box at the center where we have no idea about how it works. Those systems, most of them are considered to be black box systems. The reasoning and results are not always clear to the users, and as a result, their outputs may not be understood given the input to the system. As a byproduct of this opaqueness, these systems may be considered or may be actually in fact biased. They may, there is the risk of discrimination, there is a risk of unfairness, unfair treatment of their users, and the challenge is actually how we can ensure that those algorithmic systems are fair, and how we can ensure that these systems are also perceived fair by their users. So first of all, we will discuss a little bit risks and biases in algorithmic systems as a kind of follow-up from Fausto's discussion about biases and diversity, which is inherent in our society. And this is something that we should keep in mind all the time. We are all biased. We were trained, we were raised, we have our own cultural background, and the diversity is actually the main reason for bias, even if we are considering ourselves as non-biased people. So biases may be exhibited by an algorithmic systems, and in general, they affect the output. Whatever happens, the results are reflected by the output, and we call it an algorithmic bias. When we discuss algorithmic bias, we try to split it into several categories so we can reason about, first of all, the biases and their characteristics, and later on, how to address them. And we are looking at three different types. We are looking at bias, which is a result of the data that the system has been trained on. We are looking at bias, which is a result of the algorithm itself, and we are looking at bias, which is the result of the humans that are involved in the process of the system. When we're considering the data, first of all, we have the users, the training data that has been used to train the system. How training data is being collected? Training data is being collected by people that are building the system, that are building the data set that it used to train the system. Those developers or users may or may not be aware of the target population, the population that will be the one that will use the system, or that the system will be used to provide services to this population. So if the training data does not represent the target population, then the results may be biased. Moreover, training data usually is something that is being tagged in cases by users. We may use mechanical markers to tag and annotate information that is used later on fed into a system to train it, and those annotators may be biased. We may use historical data to train the system, and historical data may reflect historical biases. In the past, if we are looking at various professions, well, if we're looking at mechanics, usually there were men. And if we're trying to train the system to identify mechanics, if we're using historical data, probably men will be the majority. So the definition of a mechanic will be biased towards men. Another issue is the input data. Whatever we provide the system as an input may be considered and reasoned about. And if we provide information that in some cases may be irrelevant, like a gender or a race, when there is no need for that, and this is something that may cause bias in the reasoning process. Another aspect is the algorithmic process itself. The algorithm is the result of a programming process. The algorithm itself may be wrongly programmed, may have errors, may cause bias just by the processing process of it. So this is another source that we may consider as a bias. And related to it, and a bit different, there is human bias. As already noted, we are all different. We come with different background and different knowledge. And even without knowingly, we may be biased. And this bias comes into effect when we develop systems. This bias may be reflected in the programs we write, or this bias may be reflected in the configuration, the way we configure a system. And we may configure a system intentionally or unintentionally. I may prefer to hire young workers which are not female because female are having children, they take long vacations, they are absent many times due to the need to treat their kids. And this is an intentional bias that may be introduced into a system as part of its configuration. So there are three different types of biases that we would like to find out how to address. And if we are considering now the model that we introduced earlier, we can see how these different types of biases fit into different aspects of the model, and how all of them individually or combined contribute to the algorithmic bias which is reflected by the output of the system. If we are looking at Sorry about that. This is the result of using a computer that I'm not used to operate. So if we're looking at a job filtering system, we may see that the training data may be a set of candidates and their job applications and whether they were selected or not to specific positions. Now, a bias that may be introduced there, we can take like the gender bias. If the majority of the candidates that were selected for a specific position are men, and the candidate that is applying to the job is a woman, then potentially she will be rejected just because the training data, the vast majority were men. Or maybe that the candidates and then the application and the training data is perfect. They are balanced and there is like 50-50% representation of women and men for specific job application. But then the company guidelines are prefer, if you have candidates with similar capabilities, prefer men if you have men, or give women a lower score just because this is what the company decided to do. Fair or not, this will be reflected in the output, and this is something that represents an unfair behavior of a third party. And eventually, if there is a vast majority of candidates that were rejected and they are living in a specific region, which has nothing to do with their level of qualification, whether they fit or not the job, if the system was trained with a large number of applications that were denied and all are from a specific region, maybe when the candidate provides an application and the region where the candidate comes from is the region where most of the candidates were rejected, this may have an impact on the decision of the system. Again, an unfair behavior, which is the result of the input data that has some irrelevant information included in it. So how can we deal with it? We have seen that we have several types of potential biases. And first of all, we can think about objective and measurable manners that will enable us to examine the fairness of a system. We can think about techniques and predefined sets of examination techniques that in specific data sets and representing input information to check and see whether the system works in a consistent way, whether it is does not the rules that are applied by the system are applied equally to different types of applicants, and the system is fair. When we talk about fairness, we may talk about what is called individual fairness, that any two individuals that have the same characteristics are getting the same results. So people with different characteristics are treated similarly. And there is another type of fairness, which is group fairness or group parity or demographic parity, which means that the proportions of success or failure are similar in different groups or different populations. So a specific population is not discriminated compared to other populations. So let us take a deeper look into formal solutions. In order to be able to ensure or to check whether a system is formally fair, we need to have some objective, measurable fairness measures. And what we need to do is to have two types of treatments, two types of approaches. First of all, we need examination methods, ways to verify and check that the system is indeed fair, to detect whether the system is biased or not. And in cases we detect that the system is biased, then we need to find out how to improve, how to mitigate the discrimination or the unfairness. So when we talk about formal fairness, we need to do several things. First of all, we need to decide, we need fairness formalization, we need to decide how we are going to deal with fairness. Then we need to find out or define techniques for discrimination discovery to check whether the system is actually discriminating. And here we can have, we can consider explicit or implicit discrimination. As we already discussed, systems may be discriminating either intentionally, if they were configured or programmed intentionally to favor specific characters, specific characteristics or populations, or simply by using a biased training set or bringing into the development or configuration process individual points of view, individual cultural background, which is discriminating. So fairness formalization we discussed. We said we may consider individual fairness or group fairness or a combination of both. Discrimination discovery we discussed, and then there is auditing, which actually it's the same as discrimination discovery. It is meant that auditing is done by an external body to ensure that the system is fair, unlike discrimination discovery, which is a general set of techniques that may be used either by developers, whoever is going to use the system, or by external bodies. By the name of auditing, means that an external body is doing the examination and ensures that the system is fair. Assuming that the system has been found to be unfair, from some reason certain groups of in the population are discriminated, or genders, or people that have specific characteristics living in a certain region or speak a specific language, whatever it is, assuming that discrimination has been discovered, then there are two aspects to consider. First of all, we need to check the training data and to see whether the result of the unfairness is represented in the data. When the system is, the algorithms are okay, everything is fine, but the training data is biased, and this is why the system or the model that has been developed is an unfair, a discriminating one. So we can use techniques to balance the data set, find out those features that are causing the discrimination and either eliminate them or balance the data set so people and populations will be treated equally. And if the data set is fine, then we need to check our algorithms or the learning mechanism, and to ensure that the model that is being learned is learned and configured not in a way that actually biases the system. If we are now looking at the job filtering system, we can summarize the process of the formal fairness process as follows. When we are looking at the data set, we may need to ensure that the data set is balanced to represent correctly the population that will be treated by the system. Obviously, this is common knowledge for any machine learning application, machine learning developers, but apparently sometimes this is something that goes unnoticed, and the system is being trained and used, is trained on one type of data and used on other types of population, and there are quite a few well-known cases like this. If we are considering, for instance, medicine, in the past, the cardiac arrest symptoms were according to white males' symptoms and not women. So those kind of heart attacks on women were unnoticed or less identified than men, just because all the studies and the guidelines that were developed were based on men. So we are talking about the data set that needs to be balanced. We are talking about the individual fairness, the ensuring the two people of the same qualification may receive the same recommendation score, so we can actually prepare a set of different candidates' applications and check that those conditions apply. If we're talking about formal fairness, about individual fairness, then different people with different personal characteristics, but with the same relevant qualifications for the job, get the same score or the same recommendation. And if it does not happen, then we need to check either the data set or the algorithm or both. And we are using this kind of a diverse set of applications in order to ensure that the system treats them fairly. And we can use it also for a group fairness if you'd like. We keep several populations and mix them and try to see that the proportion of rejection and acceptance is similar in the different population. And for that, we can apply these discrimination discovery techniques, either internally within the company or externally auditing by any kind of regulator to figure that out. Now, the big question is that enough? When we do the formal checking of the system, is it enough? And being human, I would say that it is not really enough, because there is our personal subjective perception that gets into play. And let us consider a little bit about the issues of perception. And we are defining perceived bias as a bias which may be the result of the subjective perception of the user that considers the system output, maybe with respect to the input, maybe with respect to the way the results are presented, maybe due to lack or having less or more knowledge about the domain or the way the system works, or simply based on diversity of users and their point of view. We all know that the way the system interface looks, the way we are getting the results, the way things are presented or displayed to us, impact the way we are consider the system to be better or worse. And there is no difference with respect to fairness perception. And we carried a series of small-scale experiments in order to demonstrate and show that. And a very simple one and a trivial one was an experiment we carried out in one of our classes, and we simply asked the students, well, you should say yes or no if you would like to get 10 points added to your course grades. Obviously, that the students would say, everybody would say yes, right? So this was the first system, the first experiment, an imaginary system that will provide the students additional 10 points, and all they need to do is say yes or no. And then we presented another system that does the same, but there's an explanation. Only one winner. The winner will be chosen according to the number of people who voted yes. You can only win if you are the only one who voted yes in the last day. So there are two systems, and if we are looking at what people thought about the system, obviously, in the first step, about 41 students out of the 52 decided to play the game and voted yes. Obviously, nobody got any point because the system gives points only if there is a single person that votes yes. And 27 students complained that the system is unfair. However, with the second attempt, when there was an explanation about how the system behaves, only 7 students tried to get the extra 10 points. Obviously, no one got points, but only 3 students said that the system is not fair. So we see here that the simple explanation, a very trivial example, makes a difference. So this is something only to demonstrate the idea that there is a way to change or manipulate the perceived bias of a system. And this is something that you should also be careful about, because we don't want to convince users that an unfair system is in effect a fair one. So perceived bias may affect the input that the user provides to the system. Users may provide incorrect and incomplete information in order to manipulate the system. Perceived bias may be affected by the process of the system as represented or presented by the output and the reasoning of the users about the correlation between the output and the input of the system. So let's look again at our model, and we have the input and the third party and the training data and the output, and we have the perceived bias, which is actually the perception of the users given the input to the system, the results, and what the user thinks about the correlation between the results and the input. And this is something that we'd like to address and help users reason about and convince them whenever there is a fair system that it is actually fair. So we are talking about what we call informal fairness. And informal fairness addresses the subjective point of view, personal point of view of users, how they perceive the system behavior. And we are considering several points of view may be part of it. The perception of the perceived outcome and its distribution. So how the users are perceiving the output with respect to the distribution of the results in different populations. So this is something that is similar to the group fairness that we discussed earlier. There is a procedural fairness, how the users are perceiving the process of the reasoning or the decisions that were taken by the system or by the process. The perception or the perceived bias does not necessarily apply to black box, to algorithmic systems, but in general to decisions taken about users. But we adopted it for the systems, for our algorithmic systems or reasoning about algorithmic systems. Informational fairness, it's about the amount of information and explanation that the user got about the results, the process, and how the output was reached. Interactional fairness, this is something that does not appear usually in black box algorithmic systems. It is about the interaction with the person, with the process, with the system, and how the user, and usually this is something that has to do with interpersonal interaction when a person is treated by a human, and how the interaction goes and what is the perception of the user about the interaction itself. So this is something that when we're talking about the system, simply about how the system presents the information. So we can, when we talk about possible solutions to the informal fairness, the only real things are related to, first of all, examination methods. We need to be able to examine whether the system is perceived to be fair or not by the user, and in case of not, what can be done in order to mitigate this perceived unfairness. So we are talking about improvement methods. And when we're talking about informal solutions, we are talking about examination, we are talking about perception. When we're talking about examination, it is simply using questionnaires, interviews, trying to get the point of view of the individual perception about the input-output ratio, what they think about the algorithmics, the quality of the treatment they got, explanation provided, so anything that has to do with how they perceive the system, the output, and the correlation between the input and the output to the system. Simply get the information from the users. Then, assuming that the system is perceived to be unfair, we would try to improve the fairness perception. And this can be done in two different ways. One is the issue of explainability. If we would like users to perceive a system as fair, we better explain why an output has been reached, how it has been reached, whether it is distributed or how there is the correlation between the data and the characteristics and the output, how is it happening, whether it happens similarly in different populations, and how it can be examined or presented. When we're talking about explainability, then it is claimed that explainability contributes to transparency. If we provide explanations, we make the system, the black box, a bit more transparent, and transparency supports the perception of fairness. And also explainability directly supports the perception of fairness. And another point of view is certification. But just before we get into certification, maybe we get a little bit into more details about explainability and looking into the black box. When we're talking about machine learning techniques, there are maybe two types that we may consider. There are black box machine learning algorithms, which include mainly deep learning, but also support vector machines and others when there are large numbers of features involved in the process. And there are white box explanations, and white box algorithms are those that the reasoning process can be easily traced. And if we are talking about a decision tree, we can go from the root all the way to the leaf and figure out what decisions were taken in every step and why a specific decision was reached. We can do the same for decision rules, which actually is another way to look at decision trees. We can look at Bayesian reasoning, Bayesian networks. So those are examples of algorithms that the reasoning process can be traced and explanations can be easily provided. While when we are talking about black box explanations, this is quite challenging. We're talking about black box explanations. We're talking about explanations about how the model is working, how the model works, and we are talking about how the outcome has been reached. And when we are talking about black box, one way to do it is to use a large number of results, meaning that we have the input and we have the result provided by the black box. And once we have a large set of cases like that, we can try and reproduce the reasoning process by applying a white box machine learning process like decision tree or decision rules on the same data, trying to infer implicitly or infer the implicit rules that were applied by the black box by training a white box algorithm and reasoning about that reasoning process. So this is one approach that is being suggested to kind of open the black box and make it more transparent. Certification is simply the process of ensuring that the system is fair by auditing by an external body that we all trust, like the VeriSign signal or the VeriSign symbol that we see and when we pay using any kind of e-commerce website, and we can trust the payment system, and we can provide our credit card number and rest assured that it will not be stolen. Here we also did a couple of experiments to understand what is the perception of users about different measurements, different types of fairness. So we wanted to see the importance of fairness definitions, and we wanted to see how explanation impact the evaluation, whether or not explanations impact the fairness, what kind of explanation impact the fairness, and whether explanation help user understand system outputs. So we had a large-scale experiment with mechanical Turkers, relatively large scale. We had 3 different experiments. One was a set of fairness features that we asked the user rank in order of importance. Another, we asked user to let us know which feature they will give up first, so rank them by the order of what they are willing to give up. And the third one was about pairwise comparison of different types of features. And what we try to compare is 4 different types of feature: the distributive explanation, the procedural, informational, and interactional fairness. We try to see which those perceptions are preferred by the users and which is less preferred, and we try to look both at individual fairness and group fairness. And what we noticed was that things that has to do with group or distributive fairness were considered the least important, and the individual fairness, so actually that users, that the personal things that are more close to the person itself, individual fairness and procedural fairness are considered the most important, while the interaction were kind of in the middle. So the conclusions were individual fairness and procedural fairness are the most important one. Group fairness, distributive fairness, from some reason, were considered less important. And it is interesting to note that they were correlated with what is called self-love theory. That people like themselves. The second experiment evaluated the user's fairness perception, the impact of explanation on fairness, and the level of understanding. And users were presented with the results of a hiring of an imaginary hiring system, automatic hiring system, which gets a description of a candidate and may provide a recommendation to recommend or not recommend a candidate. and we had 5 styles of explanation, a case-based, one that said in a case similar to this, then the result was like that, a demographic-based, groups and population in the explanation about the population, input, explanation about the specific characteristics or specific features that led to the decision, and certification-based, whether the system is got a certification to be a fair one. Well, I guess the numbers are less relevant, but the conclusions are more relevant. And it is interesting to note when the system declined or rejected the candidate, it was mostly considered unfair regardless of the explanation that were provided. And when the system provided a positive output, recommendation to consider or recruit the candidate, it was considered fair regardless of the explanation that information that was given, with a slight advantage to the certification-based explanation. It is interesting to know that explanations were considered helpful in understanding the output of the system in both cases. So this result also calls for additional research. And now let us summarize what we discussed so far. First of all, we can see that if we are considering system which is formal fair and informal fair, this is the best case. If a system is formal fair and formal unfair and informal fair, this is something that is not desirable, and you should be aware not to mislead users about unfair system and convince them that they are fair. This is the role of advertisers, and this is something that at least we as information systems developers and people that are actually using and developing such system should be aware not to get to. If the system is formally fair, but it's perceived to be unfair, this is something that we should try and do something. And if the system is unfair and is considered to be unfair and it's perceived to be unfair, little to do about it. So actually, if we are considering the matrix on the left, then there is the set of actions we can take on the right. So if the system is formally unfair, we can apply formal solutions or formal fairness solution to solve this problem. If it is fair but considered to be unfair, then we can try to figure out what can we do in order to persuade the users in the fairness of the system. And if it is considered to be unfair and it is formally unfair, then we need to work on both aspects. So actually what we need to do is get systems to be first formally fair and finally perceived fair. So this is something as kind of a fairness pipeline we suggest. So once you have a system, first you need to check and ensure that it is formally fair. If not, you fix it. Once it is formally fair, then you check if it is perceived to be formally fair, and if not, then you apply informal fairness improvement methods until you get it to be formally fair and informally fair. And I guess that I saved a few minutes and got us back into time, and thank you for listening.